Hello everyone, this is Muhammad Al-Hussein. In this video I will show you how reinforcement learning can be used to solve the dynamic taxi dispatching problem. The problem is defined as follows. We model the city as a rectangular grid. We have fixed number of taxis that are distributed on the map, and passenger requests merge stochastically on the map. Our goal is to assign taxis to requests in a way that minimizes the waiting time for customers and also minimizes the distance traveled by the taxis. So first we need to formulate the problem as Markov decision process, or to be precise, as a Markov game, because we have multi-agent. We don't have one taxi, we have multiple taxis. So we need to define the Markov game formulation for our problem. So it's defined by the following tuple. N is the number of agents, i.e. the number of taxis. S is a state space. A is the action space. P is the transition probability function. R is the reward function. And gamma is the discount factor. So the environment state space variable encodes the information that will help agent to make the optimal decision regarding the problem of concern. Our state variable is encoded into a 4D tensor, image-like format with 3 color channels, as shown in this figure. So the first channel will encode the location of the agent itself, the taxi of concern. The second channel will encode the location of other agents, other taxis. The last channel will encode the location of the requests. This is the action state. This is the action space for each taxi. One of the 5 possibilities: either the taxi stays on the same cell, or move up or down, or left or right. We don't have diagonal movement in this formulation. So after formulating the problem as Markov game, we define the reward function. Actually, we tried different reward configurations. We'll just say one of them. So the reward configurations, I think here. For instance, in this configuration, we penalize taxi for moving into a cell without picking up request, or staying on the same cell without picking request. We only reward the taxi when it goes to a position where it can pick up request. So this is one of the configurations. So now let's run our code and see how the training process goes. So here we set some of the hyperparameters. The grid dimension is 20, so the grid size is 20 by 20. The number of taxis is 10, and the maximum number of requests per state is 12. So as the simulation is working, you can see the initial policy. The taxis are stacking on the top right corner without picking up requests. This behavior is expected as the initial policy is random. So we can see that the average waiting time is 54. The average travel distance is 25 or 26, and the accumulated reward is about 50. For the next episode, the average waiting time increased to 90, and the reward to 79. Distance is 46. We have to wait until the taxis learn something useful. We will wait for like maybe 70 episode, 100 episode. It actually depends on the grid size, the number of taxis, the number of requests. We have to wait and see. Let's stop the recording for now. 40 episodes, you can still see that the average waiting time jumped to even higher value, around 156. The reward is 0. The distance traveled jumped to 71. I believe we have to wait for more time until the algorithm converges and the taxi learns something useful. We can see that the taxis are avoiding to pick up requests for some reason. All we have to do is wait and see. After more than 133 episodes has passed, let's see the progress of our agent. Very interesting. The average waiting time dropped to 26. The reward jumped to 475, and the distance traveled dropped to 5.7. Now let's take a closer look to see how our agents actually behave. We can see that the taxis are picking up requests and coordinating with each other to distribute requests among them. An important thing to notice is that the agents learn this policy by pure try and error. There is no explicit communication between them. The agents only see the states and the rewards we defined earlier and nothing more. This is the elegant thing about this solution. Okay, now let's plot the learning curve for the algorithm. This is the plot of the accumulated reward, the average waiting time, the average distance traveled. We can see that around episode number 70 the algorithm converged and stayed to minimum value for both average waiting time and average distance traveled. Okay, that's pretty much it. Thank you.